Welcome back, students. In this video, we're going to look at the complete E2 mechanism. In the E2 mechanism, it's different than the other mechanisms that we've looked at because other mechanisms had the ability to have additional steps either before, in the middle, or at the end of the reaction. And that really doesn't happen with the E2 mechanism. There are some other things that do happen that we need to take some time to discuss. One of the things that happens is the reaction can be stereospecific when you end up having only one proton on the beta carbon. Or if you have more than one proton, then you're going to end up with a stereoselective reaction. So I want to first talk about that stereospecific example. The requirement for E2 is something called antiperiplanar. When we talk about antiperiplanar, what we're referring to is that the leaving group and the beta proton have to be opposite in one another, yet be in the same plane. The easiest way for us to see if the leaving group and a proton are opposite yet in the same plane is when we're dealing with a structure that is a ring. In this case, I have a chlorine present, and that chlorine is going to be my leaving group. When that chlorine is the leaving group, then I know where my alpha carbon is, which is where I just put the blue dot on. And then next to that is my beta carbons. So I have a beta carbon here, and I have a beta carbon here. On those beta carbons, I have beta protons. And the beta protons are either coming out of the plane of the page or going behind the plane of the page, right? Coming out of the plane of the page and going behind the plane of the page. So if the chlorine is coming out of the plane of the page, then in order for the hydrogen, the beta hydrogen, to be opposite that, then the hydrogen needs to be going behind the plane of the page. What this means for us is if the chlorine is wedge, the proton that we're abstracting when we're on a ring needs to be dash. So this proton is one you could abstract, and this one is one you could abstract. Whereas the protons in front that are on the same face of the ring that the chlorine is are not going to be able to be abstracted. So the base is going to come in and it's going to pull off a proton. These electrons will form a pi bond and your chlorine will be expelled. And you'll end up with your alkene. Now in this case, because we have a symmetrical structure, it doesn't matter if we pulled off the hydrogen that was on the right or the hydrogen on the left, we get the same compound at the end. Let's do a little bit of a change. Let's take the structure that we have and update it. With the chlorine being wedge, remember our beta proton needs to be dashed in order for a reaction to happen. What that means is if we had, say, a dashed methyl here, then nothing could happen at that position. If we had a dashed methyl here and we added a base, then no reaction would occur because you must have the beta proton opposite of the leaving group. If we changed this a little bit and put the methyl on the left on a wedge, now we could have a reaction happen because if that methyl is wedge, that means there's a dashed proton here. So the base could come in, pull off that proton, the electrons would come around, form a pi bond, and kick out your chlorine. When we do this, remember that your pi bond is always being formed between your alpha and your beta carbon. So my pi bond is here. What didn't change was this CH3. Nothing changed. There was no reaction at that carbon, so it just stays the same. Now let's look at antiperiplanar, but outside of a ring. Inside of a ring, antiperiplanar is easier to see. When we're looking at outside of a ring, something that is a straight chain alkane, it gets a lot more difficult. When we're looking at this example, what I want to point out is the leaving group and also the beta proton. I purposefully designed this molecule so that there's only one beta proton. Let's take notice how the beta proton and the leaving group plus these two carbons, the alpha and the beta carbon, they're all in the same plane. Whereas the phenyl, which is the fancy word for benzene as a substituent, is coming out of the plane of the page. The methyl is going behind the plane of the page. Over here, this hydrogen is coming out, and this tert-butyl is going behind. In order for the E2 reaction to happen, the hydrogen, the alpha carbon, the beta carbon, and the leaving group all need to be in the same plane. They also need to be opposite one another. See how the bromine is up here and the hydrogen is down there, right? That's opposite. When we're looking at the idea of the same plane, they can be close to the same plane. So there's two words that people use here. People will say antiperiplanar, which means opposite groups that are close to being in the same plane, or sometimes people will say anticoplanar, which is two groups that are in the same plane. I utilize the term antiperiplanar, but don't be surprised if you see other resources saying anticoplanar, because it just means that those four groups are in the same plane of the page. In order for this reaction to happen, we need to have those two groups opposite one another so that the base can come in, pull off that proton, make a pi bond here, and expel your leaving group. When this happens, the key is you can really only form one product, and the wedges and dashes that you're seeing for the other groups that are present are going to dictate what your product is going to be. What I mean by that is once the hydrogen, the beta proton, and the bromine are gone, you're going to have something that looks like this, where you just formed a pi bond. But now the carbons that were your alpha and your beta carbon are now sp2 hybridized, which means they're in the plane of the page. If they're in the plane of the page, then what will happen is they are trigonal planar. They lose that wedge dash. What we need to be able to do is look at our initial structure and figure out where the groups are going to be with respect to one another. I'm actually going to erase these arrows so that I can redraw on this structure. What I see that you need to also see is there's one group that's wedge and another group that's wedge. The two wedge groups are going to be on the same face of your alkene, meaning your phenyl will be on the same side as the hydrogen. Then the groups that are dash and the groups that's dash are going to be on the same face. So you'll have a methyl here and you'll have your tert-butyl here. So there's only one possible answer. You cannot have the other form of this alkene. We can actually pause and stop and ask ourselves, is this an E or a Z alkene? So why don't you pause and see if you can figure that out. Let's talk about whether or not this is an E or a Z alkene. What I like to do when I'm looking at the E and the Z alkene is first I like to split my compound down the middle, and I look at the two groups, this one, and decide which one takes priority. When we look at which one takes priority, the phenyl group is going to end up taking priority. And then we're going to do the same thing to the other side. So the tert-butyl takes priority over a hydrogen. Remember that priority here is based upon atomic number, like how you saw with the R and S configurations. Now that I have my two groups starred, which is just me mentally keeping track of which ones have priority, I'm going to change what I am visualizing. And when I look at this now, I'm going to change my perspective and I'm going to look across my pi bond and see that I have one group up here and one group down here. So they're on opposite sides. And if they were on the same side, that would be Z. If they're on opposite sides, this would be E. So your E alkene is your only possibility as a product here. In order for you to get the Z alkene, you would have had to have this side of the molecule rotate so that the hydrogen was pointing more upward. But if that were to happen, then your leaving group and your beta proton would no longer be antiperiplanar. So it wouldn't be possible. Let's transition into stereoselectivity. If there are more than one beta proton on a carbon, then we can get that opportunity for both cis and trans alkenes, or if there are complex compounds, we would name them E and Z. Here I've changed the molecule from the last page. What I did in the change was I took the phenyl group that was here where I'm highlighting in yellow and I turned it into a hydrogen. Now that I turned it into a hydrogen, I have 2 beta protons. Let's go ahead and carry out the reaction the way that it's drawn in this particular structure. So I'm going to pull off this proton because this one is antiperiplanar, and we're going to go through the reaction this way. When we go through the reaction, remember we get a double bond, and we use the wedges and dashes to figure out where the groups are on the product. In this one, both of my hydrogens, I'm going to highlight the hydrogen in yellow, those are both wedged, so we're on the same side of the alkene. It doesn't matter if you write them on the top or the bottom, you're just writing them on the same side. So I have a hydrogen and a hydrogen. Then my dashes, my dashed bonds are this methyl and this tert-butyl. So those are going to be on the same face as well. So I have a CH3 and I have my tert-butyl. This alkene, if you'll notice, is the Z alkene. So this conformation that I drew on the left gives rise to the Z alkene. Now what I can do is I can rotate so that when I'm showing the reaction happening again, the hydrogen that I'm pointing to that's highlighted in yellow is now pointing downward. So let's go ahead and rotate that really quick. I've redrawn this structure, and what I've done is taken the left-hand side and I've gone ahead and I've twisted it so that now my hydrogen that was yellow in the previous conformation is now down here, and the hydrogen that was blue in my previous conformation is now here. And that made my methyl turn into a wedge. Now what's going to happen is the base is going to come in, it's going to pull off the proton that's antiperiplanar, the electrons will come around, and my bromine will leave. When this occurs, remember that I'm getting a pi bond. Now I need to know where my groups are with respect to one another. My hydrogen and my methyl are both wedged, so they're going to be on the same side or the same face. Then the hydrogen and the tert-butyl are dashed, so they will be on the same face. This conformation is E. When you have only one beta proton, then your hand is forced. You have to go through and figure out what the compound at the end is going to look like. If you have 2 beta protons, it becomes a lot easier because you just draw both products, knowing that the trans or the E product is going to be the major one. So you would draw both of these, and then you would call this one the major. Let's wrap up. In this video, we looked at E2 reactions. We reminded ourselves that this was a concerted process where the proton transfer and the loss of the leaving group happened at the same time. There weren't any additional steps that we needed to worry about, but we did need to take the time to remind ourselves of what antiperiplanar meant and make sure that we saw some examples where that antiperiplanar idea played out. We also reminded ourselves that if you have 2 beta protons instead of 1, then you're going to get both the cis and the trans isomer. As always, thank you for your attention. This is Katoni signing out.